this computer, and I'm sharing my screen. And hello, everybody. Good morning, everybody. And hello, everybody out there watching on YouTube. So the reading for today, we're going to look at sections 7.2 and 7.3. And on Wednesday, I think we're going to get into section 7.4 and 7.5. In case you hadn't seen, problem set 7, whose outline we sort of assigned over the weekend, is due on Wednesday. But it's just the world is on fire right now, as everybody knows, and so it's really just kind of due on Wednesday. Get it done when you can, and then so there will be an exam too. That what will almost certainly happen is that we will have 2 exams this semester instead of the originally intended 3, and exam 2 will be delayed until mid-April, which is basically enough time, I hope enough time for me to figure out how to actually administer an exam online, because I'm not really sure how to do that. But for now, the thing to think about is about problem set 7 due on Wednesday, and then I guess then spring break starts, such as it is, and so think about not going anywhere for spring break, I guess, is what we're thinking about. Any questions? Any questions so far? Anybody ready to go? Everybody ready to go, or at least as ready as you're going to be? Can you all hear my family stuff going on in the background? Now I'm curious. Yes or no in the chat box? Can you hear the family stuff going on in the background? Yes, you can hear it. Faintly, yes. Yes. So this is what everybody's lectures are like now. There's like sort of faint background chatter of like either not really or faint background chatter of like family stuff going on. This is our new reality. Okay, let's go. It's the world is going crazy, but it is kind of I mean, at least for me, it's kind of a balm to be able to go in here, and at least there's this one area of life where we have some control for what's going on. So with that, let's do some math. Okay. So last time we talked about cosets. So let me. This is where we left off. We were just getting to the idea of a coset. So let R be a ring, and let I be an ideal of R. Oh, right. I guess we should. Yes. So let me. So I want everybody to try to remember the definition of ideal. Oops, that's not what I wanted to do. I wanted to get a blue thing here. So remember, the definition of ideal has 3 axioms to it. And I want everybody to think about what the key properties of an ideal are. And just to give you a little reminder, their properties 0, 1, and 2. So everybody think about that for a few seconds, and then I'll you can start typing the chat. Then I'll say go, and you can start typing the chat box as to what the defining properties of an ideal are. I just realized what this is like, especially for those of you watching on YouTube. This is just like the part in Dora the Explorer where she says, "Can you see where Swiper went?" And then they pause for like 15 seconds. You're like, "Come on, he's right there. How can you not see him?" But okay. Anyway, so speaking of which, does anyone remember one of the 3? Want to type in the chat box one of the 3 defining properties of what makes that make an ideal an ideal? All right, so Alexa's putting property number 1, which is that I must be closed under addition. All right, this is like Family Feud. Survey says property 1 is that I must be closed under addition. You say property. Survey says I contains 0 elements?
I'm coming.
All right, somebody else want to? Oh, close under. Yeah. So John V said had got the tricky one. I is closed under multiplication, and this is the tricky one because there's actually more to this under scalar multiplication. Yes, by elements of R. Exactly. Yeah. So John V said multiplication, and Ishan completed that to scalar multiplication. Yes, scalar multiplication by elements of R, which is exactly the same thing you remember for subspaces, which is scalar multiplication. And here you want to think about the scalars come from are just arbitrary, are actually just arbitrary elements of your sort of underlying ring R. So this is the definition of what it means for I to be an ideal. All right. So again, anyway, let R be a ring and let I be an ideal of R. For little r and big R, we define the additive coset, or just usually coset for us, R plus little r plus big I to be little r plus big I is the set of all things of the form little r plus A, where A runs over all elements of I. So, and again, usually, oh yes, so since I is an R, can 2 ideals be multiplied? Oh my goodness. Ryusei asked an awesome question. This is kind of far afield from what we're doing here, but if you want to really go down the rabbit hole, because if you got a little extra time, you might have a little extra time in your hand. So Ryusei asked, oops, you want to make this blue. Ryusei asked, can you multiply ideals? And the answer is yes, but that's way more complicated than we're doing here. That's a graduate algebra topic. Google ideal factorization if you want to go down the rabbit hole. And this is actually the I can't resist mentioning that you can multiply ideals, just because that's the original. We will not do that, actually. That's not something we will do. That's not something that's relevant to our class directly. But it is something lurking in the background. That's actually the reason why the reason for the very strange name of ideal. It's because well, anyway, Google ideal factorization if you don't want to go down the rabbit hole. Anyway, any other? That's an excellent question, as it happens. Any other questions for the moment before we do an example? Okay, though I think though I want one note about what Reese said. Note that I is a subset of R, not an element of R. So you can't multiply 2 ideals in the usual way that you would multiply elements of R, but you can sort of multiply the sets. But okay, well that's the topic for another day, really more of another course. Okay, so what I want to talk about is just actually specifically examples of additive cosets. So here, remember we talked last time about the ideal generated by 3, which turned out to be, which by definition is a set of all multiples of 3. So you may remember that this is so -9, -6, -3, 0, 3, 6, 9, so on. So remember, capital I is a set of all multiples of 3. Looks like that. Right. So I want to write down one example of a coset of I, and so somebody just want to type in the chat box just any integer. Oh yeah, and oh sorry, it's very important to know for this for this and to understand what's going on in ideal, you have to sort of specify what capital R is, and here capital R is the integers is z. So somebody wants to type in a random integer, whatever you like. 25, fantastic. 25 plus 3. So yeah, sorry, 25 plus parens 3, the ideal generated by 3. Well, so by definition, what that is it's what you get when it's what you get when you add 25 to each of these elements. So actually, let me actually go back a little bit, and what I want to do is I want to sort of. So one thing that it's easy to underestimate is the fact that all what's going on with these dot dot dots. So remember, those dot dot dots go on forever, and so what they really are is that they're an abbreviation for all the other multiples of 3. So if I extend what's written there a little bit, I get minus 27, minus 24, minus 21, okay, minus 18, minus 15, and so on. So I'm going to start looking at a slightly different portion of what's going on there. But the important thing to remember is that these are really the same list. We're just sort of looking at a different part. We're just looking at a different part of the window, so to speak, on some finite number of elements in the infinite list. And so when I add 25 to each of these, I get minus 27 plus 25 is minus 2. Minus 24 plus 25 is 1, 4, 7, 10, and so on. All right. So does that make sense? How we got 25 plus parens 3 to be that list. Is everybody good with that? Say yes or no in the chat box. Say yes in the chat box or ask a question. Questions? Okay. All right. Can somebody else name a different? So give me a different integer. And so actually, what I would actually want is a different. Yeah. So that's right. So what Ishan asks. So a coset is just a shifted ideal. That's exactly right. So it's a coset is an ideal shifted by some fixed amount. You shift everything by the same fixed amount. Yes, I agree. That's cool. So somebody want to name another find a different coset by naming a different integer. Just name a different integer. Just type in any integer. There's nothing. There's no wrong answer here. Besides, no one can see the chat box in the recording, so you can just pretend that somebody else said it. Okay, 7. There we go. So 7 plus parens 3 is 7 plus, and here I'm going to use the list that we sort of had to begin with, minus 9, minus 6, minus 3, 0, 3, 6, 9, so on. Okay, so and so if I add 7, if I shift everything like as Ishan put it, minus 9 plus 7 is minus 2, and then plus 1. Is that right? Yes, that is right. So 4. Hey, look at this. This is a very familiar list of things, isn't it? 7, 10, 13. Well, so one of the interesting things about what's happening here is that this is equal to 25 plus parens 3. So and the point is that these are the same coset precisely because they're equal. They're equal to the because they're equal mod because 25 is equal to 7. Oops, I look overly excited there. Because 25 is equal to 7 mod 3. Yeah, so they're actually the same coset. And in fact, what these would normally be is they're both equal to the coset of 1. They're both equal to 1 mod 3 because they're because both 7 and 25 are equal to 1 mod 3. And so I mean, uh, so this phenomenon that we just encountered here, uh, which I'll put in this green box, is very important, and it's important. So it's very important to remember. So this is sort of the trickiest thing about the idea of coset is that different representatives. So the thing in the front, the 7 or the 25 or the 1, we call a coset representatives. Different representatives can give the same coset. And in fact, what we'll see is that any two numbers that are equal mod 3, when you sort of add them to the coset parens 3, you get the same. You get exactly the same coset. So in fact, oops, undo. So in fact, there are exactly 3, no coincidence, cosets of parens 3. There's parens 3 itself, which is, you can think of as 0 plus parens, as Ishant put it, parens 3 shifted by 0, and then parens 3 shifted by 1, and then parens 3 shifted by 2. Actually, let me introduce a bit of notation here that we'll use quite often. It will often actually be sort of, I apologize for erasing here, but fortunately, since you have this on YouTube, you can always sort of go back and fix this yourself. There are 3. So if I equals parens 3, so just so I don't want to keep saying parens 3 all the time, the cosets of I are I, 1 plus I, and 2 plus I. And we'll come back, and we'll come back to this later. What's a representative? The thing in the front. So for now, yeah, Ishan, you caught me. I kind of introduced something before I really defined it, but we will later see that that thing in the front, the 7 or the 25 or the 1, is called a coset representative. A coset representative is the chosen shift, is the shift that you've chosen to explain what that coset is. And as we'll see, there's sort of different. One of the reason I keep talking about representatives and shifts is that there are different choices of shifts that are possible. Yes. So right. It's a representative is the shift that you have chosen, and 2 representatives have the same coset if they end up having the same effectively the same shift. Yeah, Ishan, excellent questions. Thank you. Okay, so speaking of which, so the question is the question that arises from this. So we have the circumstance here, and we have 7 plus parens 3 is equal to 25 plus parens 3 is equal to 1 plus parens 3, and so we have a general question of when it is so let R be a ring, let I be an ideal of R, and let little r and little s be elements of big R. Then the question is when do 2 representatives give the same coset? So that's really what we're getting at, both with this example and now definitely with this theorem. The question is, when do two representatives, I'll try this, when do two shifts, oops, I was captured on YouTube forever, huh? Give the same, there we go. When do two possible shifts produce the same coset? So this is really, so what, so yeah, this theorem is really answering a question, and that's the question. When is it that when you have two apparently different shifts that actually, in actuality, produce the same coset? So that's condition one. And so that's equivalent to three other things. So that's condition one is that the cosets r plus I and s plus I are the same. Condition two says that happens when r is contained in the coset s plus I, or equivalently, when the difference of r and s is an element of I. Oops. An element of I. Yeah, so another way again, a different way of expressing exactly that same condition is that when the difference of R and S is an element of I. And finally, when the fourth condition, equivalent condition, is when R is equal to S plus A for some A and I, which, if you remember, that's the definition of being congruent mod mod 3. So this is sort of like saying that R and S are congruent mod I, which is sort of a thing I'm defining right here. So so if any of these last three conditions, 2, 3, and 4, that if R is contained in the coset S plus I, when the difference of R and S is an element of I, or if R and S are congruent mod I, this is actually sort of the definition of R and S being congruent mod I, then R plus I and S plus I produce the same coset. Okay, and right, you can sort of see that here. Here, if you go back and look at our example, 25 minus 7 is 18, and 18 is an element of that coset of that ideal I. And so, yeah, that's one way of figuring out that 7 plus parens 3 is going to be equal to 25 plus parens 3. Here, actually, remember we saw that we wrote out 25 plus I is equal to this stuff, including 7 over here. That meant that we knew for sure, thanks to the theorem that we're about to discuss, then we know once we see that 7 inside 25 plus parens 3, we know for sure that 7 plus parens 3 is going to give us the same results. And we already discussed the fact that 25 and 7 are congruent mod 3 means we know that we're going to get the same results. So these that's exactly so this theorem sort of generalizes just the example they were looking at. So just to give you some idea of what's involved in proving that 1 implies 2, well, let's see if I can enlarge this box. Great. So the assumption for that is that suppose that R plus I equals S plus I, i.e. These two sets are equal. And we want to conclude, oops. Oh, I see why that did that. I took that a bit too far there. Oops. Let's try that again. So assume that R plus I equals s plus I, i.e. those two sets are equal. So that's our assumption. So if we're going to prove that one implies two, we're going to assume condition one, and eventually we will conclude that what's condition two? Condition two is that R is an element of S plus I. All right, so yeah, so you're gonna do I think you're either gonna do two implies three or four implies one on the homework. So are there any questions about how proving that one implies two means that you assume R plus I equals S plus I, and eventually you want to conclude that R is an element of S plus I? So there, managed to push this where you actually see all the conditions at the same time. Good so far? Okay, so to say, we want to show that R is an element of S plus I. So, but because these two sets are equal, what we really want to show is that R is contained on that left-hand side. And why is that? Well, since 0 is an element of I, and R plus I is, thank you, Ishant, I shifted by R. R plus 0, which is equal to R, is an element of R plus I, capital I. But the set R plus I is the same as the set S plus I by assumption. And so R, little r, must be an element of S plus I. So yay, we're done. So, we good? Does that make sense? Does it make sense, or you get questions? Please either say yes in the chat box or ask a question in the chat box. Yeah, I think on the homework, okay, at least everybody's willing to surrender. And the homework, I think I probably assigned 4 implies 1, which is similar, if a little, it's just slightly more involved. Okay, so anyway, so so these are all. Here's 4 different ways of looking at the condition of when two cosets are equal, and we'll come back to that. Okay, so now I'm going to define the quotient. What a quotient ring is. Quotient rings, i.e., what was really going on here, i.e., we're going to finally define Z mod 3. Yeah, so I mean, I hope by now that everybody kind of accepts what Z mod 3 is. It's, it's the integer, which is what you get when you take the integers and set 3 equal to 0. But if you're a stickler for precision and rigor and yada yada, then it is only right now that we're defining one of the first objects we saw in the course, Z mod 3. Okay, so well, not one of the first, but within the first 2 weeks of the course. So the idea of so if I is an ideal, if capital R is a ring and I is an ideal of R, the idea is that we define R mod I. You take R and you set capital I equals 0. So, like I said, let R be a ring and let I be an ideal of R. We define the quotient ring, R mod I, as follows. So when you define a ring, you have to do 3 things. and then there's some sort of subsidiary things that you do. You have to define what your set is, like what is the set of things that you're going to add and multiply. You have to define how to add them, and you have to define how to multiply them. Okay, and the sort of the reason we would spend all that time fussing about coset represent so the elements of R mod I are exactly those cosets of I in R, but the tricky thing is if you look at, oh good, and I actually fixed that typo. There used to be a horrible typo in here. If you look at what's going on, so if you look at this definition, R plus I plus S plus I is equals R plus S plus I, and sort of the analogous thing for multiplication. The point is that the sum and the product of two cosets is defined in terms of the sum and the product of their representatives. So, and because we already know how to add two coset representatives because they're elements of R, and we know how to multiply two coset representatives because they're elements of R. But we don't sort of at first know how to add and multiply cosets as a whole. And so what we do is we define the addition and multiplication of two cosets in terms of the addition and the multiplication of sort of suitably chosen representatives. All right, so once we do that, then the zero element of R mod I is the coset 0 plus I, or just the coset I itself. So this is what I mean when I say this is what I mean by setting I equals 0. The point is that the way we've defined our ring, our quotient ring, R mod I, is to literally define I to be the 0 element of that ring, and the element that we call 1. Remember, when I say a 1 element, I really just mean a multiplicative identity. This is when I say a 1 element, I mean i.e. a multiplicative identity. As we'll see, is the coset 1 plus I. So all right, well, whatever. So there's so the set is the cosets, and addition and multiplication are defined in terms of representatives. So now we get down to brass tacks. So I want everybody to think about what are the elements of Z mod parens 3. Can somebody name? Oh yeah, and so here we're taking I equals parens 3. So instead of writing and saying parens 3 over and over, I'm just going to write the letter capital I. Okay, so again, that having been established, what are the elements of Z mod parens 3, Z mod 3? Oh yeah, 0, 1, 2. Okay, so everybody says 0, 1, 2. Okay, so right. So in terms of the way we defined them before, it's 0, 1, and 2. And so but that was actually, so my confession now is that was a bit of a shorthand. So in terms of 0, 1, 2, so instead of writing the 0, 1, 2, and we will go back to that notation eventually. What we're really doing formally now is that what we used to call 0, 1, and 2 is really an abbreviation for the cosets 0 plus I. Let me actually go back and sort of look at, so what are the cosets for when I equals parens 3? What are the cosets of I? They're I, which is 0 plus I, 1 plus I, and 2 plus I. And so just, if you want to be totally a formal stickler about things, and which we are being now right now. So the three elements of Z mod 3 are, technically speaking, 0 plus I, which is I itself, which is sort of all of the integers that are equal to 0 mod 3 at the same time. So yeah, so technically speaking, if you want to say what are formally the elements of Z mod 3, well, one of those elements is actually the coset 0 plus I, which is actually all of the elements that are 0 mod 3 at the same, all of the integers that are 0 mod 3 at the same time. Now, of course, if you're going to, actually do computations or actually do something with these things, you wouldn't want to actually write 0 plus I all the time. You write out all those elements, so you just abbreviate that as 0 plus I, or if you're being a little bit loose, like as we are usually, you just write out 0. But technically speaking, in the formal definition of Z mod 3, that is one element of Z mod 3. And similarly, another element is 1 plus I, which has these numbers in it: -2, 1, 4, 7, 10. And the last element of Z mod 3 is the coset 2 plus I, which has exactly these integers in it: 2, 5, 8, 11, and so on. Okay, so yeah, strictly according to this formal definition, the elements of R mod I are the cosets of I and R. The elements of Z mod parens 3 are exactly the cosets of parens 3 inside the integers, and we saw earlier that that's exactly these three cosets. So is everybody good with this, okay with this so far? Okay, so now let me draw the multiplication table of Z mod 3. This is multiplication. And so the rows and columns will be indexed by the elements of Z mod 3. There we go. And now, so what happens here is that we're gonna fill in these. So I want to sort of get to the interesting part first. So remember, by definition, multiplication of the product of two cosets is defined to be the coset that you get by using the product of their representatives. So by definition, I'm going to march down this column, because this column actually has sort of the most interesting thing that happens here. So 0 plus I times 2 plus I is by definition 0 times 2 plus I, which is equal to 0 plus I. And in fact, I know that the problem, I'm sure that was not at all obvious where that came from, but again, the frustrating, if correct, answer, like where did I get the 0, that 0 plus I times 2 plus I is equal to 0 times 2 plus I? Well, it's by definition. Because it's what it says right there. To multiply two cosets, you multiply the representatives, and so I multiply the representatives, and I get 0 plus I. In a similar way, we get 0 plus I over here, and 0 plus I over here. And in fact, I might as well go down this column here too. You get 0 plus I in every entry where one of the factors is 0. So good so far. Any questions so far? Okay, so now when I have 1 plus I times 2 plus I, somebody want to type in the chat box what I'm going to get over here? Well, okay, so let's see. So remember when I multiply, so before we get to the answer, so let me say, so remember when I multiply, oh, I want to make this a star. So remember this is multiplication. So remember the coset that I get by multiplying 1 plus I and 2 plus I is the coset whose representative is the product of the representatives. So yeah, it's 2 plus I. That's right. So thank you, Ishant. So yeah, what you get is 1 times 2 plus I, which is equal to 2 plus I. Okay. So any questions so far? So sort of, I think, nothing quite so surprising yet. Okay, so it's in the lower right here that we get the actually truly interesting box. So when I multiply the coset 2 plus I times the coset 2 plus I, what I get is I get the product that I get is the coset that comes from the product of the representatives 2 plus I, which is 4 plus I, and which you now might object, hey, I thought you said they're only. Yes, that's exactly right, Ishan. But we're getting there. But hang on. That's yeah. So Ishan has correctly surmised that this is going to be 1 plus I. But okay, well, let's get there. But you might object at this point, like, hey, how did I get a 4 plus I? I thought they're only elements of this this ring were 0 plus I, 1 plus I, and 2 plus I. But aha, I say. So because let me note over here. Because 4 is an element of 1 plus I, that means, that implies, yeah, so why did we do all this nonsense about when do two elements produce the same coset? Why do we do that? The reason is for exactly this calculation here, because 4 is an element of 1 plus I, right? That was condition number 2 over here. 4 is an element of 1 plus I. That means that the cosets 4 plus I and 1 plus I are equal. So 4 plus I equals 1 plus I. Yeah, because 4 is an element of the coset 1 plus I, 4 plus I is equal to 1 plus I. And so this is actually secretly 1 plus I. Or I mean, not secretly, but yes, exactly right, Ishant. That bottom right-hand corner is exactly 1 plus I. And so we can abbreviate. So let me use a different color for the abbreviated table. Go back to green. So we can abbreviate the multiplication table of Z mod 3 as follows. Well, instead of writing all those plus i's, we can just write the representatives that of each coset. So this is 0, 1, 2 times 0, 1, 2, and we have 0, 0, 0, 0, 0, 1, 2. Oops, I'm getting too excited here, so I'm not drawing so carefully. Good enough. 2, 2, and then we get a 1 over here. Okay, so yeah, so if you complete that table and then you draw everything in carefully, this is what you get. And so this is in fact exactly the same old multiplication table of Z mod 3 that we had back in chapter 3, I think it was. Okay, so yeah, so that's what happens if you abbreviate the red table by sort of tossing out all the plus i's, and I guess I might as well finish the red table while we're at it. Then you get exactly the thing that we had before. Yay! we have now finally justified the multiplication table of Z mod 3. Whew. Okay. Are there any questions so far about this one so this is a very specific example in the multiplication part of the definition of R mod I. So let me actually, I know this is dangerous because I messed this up. I've messed this up before. So let me go full screen here so everybody can look at this, the entirety of this example. So are there any questions about this example before we move on to checking one very important thing? Oops. Okay, and yes, I don't know why. I did that like last week, and somehow escape didn't work. But now somehow I know what I'm doing better, and so it works now. Well, anyway, so the one thing that we have to check is that R mod I is actually a ring, right? So we had all those axioms of a ring, and so now, well, and we define this. We define this thing that we hope is a ring, that's called R mod I, and the elements. And so we have elements. They're the cosets of I and R, and we define the addition in terms of representatives, and we define the multiplication in terms of representatives. And the theorem is that it works. That we do in fact, i.e., R mod I is actually a ring. So, honestly, I'm not sure. I would not expect necessarily that anybody would come up with this answer. This is a pretty deep thing to think about. So the question is, what could go wrong? What could, that is, why wouldn't R mod I be a ring? So anybody want to hazard a guess as to? So we made this definition. We defined this wacky notion of addition and multiplication, and the question is, why would that not produce a ring? Anybody want to hazard a guess as to what could go wrong? So two good surmises here. So if a sum or product of elements of the ring were not also in the ring, and that's a wow. Okay, well that was actually the one I thought that who's going to guess that? But yes, that's exactly right. So that's a hard. So kudos to Alexis for surmising that is the deal. So let me do this sort of. So there are two things that could go wrong. So why would our let me do thing number 2 first, because thing number 2 is that the axioms, the addition and multiplication do not satisfy the axioms of a ring. Exams. I have exams on my mind. Sorry, I know what you do too, but axioms of a ring. And that will actually, I'm actually going to have you doing the homework, because that's relatively, I mean, it's not easy, but it's relatively straightforward. You don't have to do something do something kind of creative. The hard part is exactly what Alexa is saying, like what if our multiplication is addition and multiplication are bogus. Geez. Do people know what bogus means? Maybe your parents say bogus. Maybe your parents are I think your parents are about the right age to say bogus. Anybody who's seen Bill and Ted? Bill and Ted's Excellent Adventure? Just say yes or no in the chat box. Bill and Ted? No? Oh. What are they teaching you kids these days? Oh, that's okay. Yeah, Bill and Ted's. So for bogus.
Bogus, I think, just means it's the opposite of good.
Thank you, Hazel, my daughter, just in the background saying like bogus means fake. Yeah, so bogus means fake. See Bill and Ted's Excellent Adventure.
No, see, Bill and Ted's Bogus Adventure.
Well, that's the sequel, but they say bogus all the time in Excellent Adventure. Anyway, I strongly recommend it if you haven't seen it. It's a fine time. Anyway, so yeah, so what happens if our addition and multiplication are bogus? So here, bogus could mean that, as Alexis suggests, that the product, the sum or product of two ring elements is not actually in the ring, of two elements of R mod I is not contained in R mod I. That's actually okay because the right-hand side of that definition is actually a coset, and therefore by definition in R mod I. So yeah, so it's not quite that. So kind of by definition, you're not going to be quite that bogus, because this stuff. Yeah, so we might worry that, like, well, are these actually in R mod I? These are cosets, so they're in R mod I. But here, the bogosity, as people of my generation would say, is a little more is more subtle. The bogosity to worry about is actually even more subtle than that. To worry about is the definition of, for example, R plus I times R times S plus I depends on the choice of coset representatives R and S. What happens if a different choice gives a different answer? Yeah, so exactly the bogosity that we have to worry about here, like exactly what is it that can go wrong, is that the definition appears to depend on the choice of coset representatives, and so we have to check if a different choice gives the different choices give the same answer. So if I can get this text box to expand, let me talk about. So let me address that concern. So suppose we choose different coset representatives R prime and S prime such that R plus I equals R prime plus I and S plus I equals S prime plus I. Yeah, suppose because remember, like I said, the whole point of that definition of multiplication, is that multiplication here, of addition up here and multiplication over here. The whole point of this definition of multiplication, for example, is that the product of these cosets, of these large infinite sets, is defined by picking one element from each of them and kind of randomly, and then multiplying those two elements together. And so that's the thing we have to worry about. So let me now address the fact that address that concern. So as we saw up here, oh my goodness, what is that? There we go. That's better. No. Here, cosine conditions. All right. So when is it that r plus I is equal to r prime plus I? Well, so one time when that happens is that one of those things is equal to the other plus a for some a in I. So over here, by that, by that coset conditions theorem, we see that we have that r prime is equal to r plus a, and s prime is equal to s plus a plus b for some elements a and b in our ideal I. So that's so remember that's exactly the time when r prime plus I is going to be equal to r plus I, and s plus I is going to be equal to s prime plus I is going to be equal to s plus I, when those two representatives r prime and r, or s prime and s, are differ by an element of I. In that case, then checking multiplication, which is the more interesting of the two cases, see the textbook for the check that addition works. We see that r prime times s prime is equal to r plus a times s plus b. Oh yeah, and remember, the axioms of a ring are just sort of basically just enough to allow you to use FOIL. So we get rs plus ar plus ra plus sb plus ab. But a and b are elements of I, and I is closed under and multiplication by elements of R. So RA and SB and AB are all elements of I. So RA plus SB plus AB is also in I, because I is closed under addition. Look, if you think about this, we actually have now used all of the defining conditions that make an ideal an ideal. We use closed under multiplication by elements of R. We're using closed under addition. So what we see is that r prime s prime equals rs plus an element of I, which means that r prime s prime plus I equals rs plus I. And therefore, the product r plus I times s plus I doesn't depend on the choice of representatives R and S. Phew! All right, that's about that's about as deep a proof as we're going to get. I didn't want to do that. No! What is redo? Oh no, that's terrible. Redo. There we go. Phew. So anyway, the point is, we're done. That's actually the hard part of the proof, and the sort of more straightforward parts of the proof I leave to you in your homework. Okay. Anyway, so that's kind of deep. We'll go back to being more calculational in a minute, but for now, are there any questions before we move on? Okay, in the remaining 15 minutes, what I want to do is I want to talk about something very, very practical. Well, I don't. It's very calculational. It might not sound very practical. Oh, can I explain the FOIL part? Uh, okay, so right. So if we had R plus A times S plus B. So Ryusei asks, can you explain the FOIL part? So you mean this? So you mean the part that starts out like this? Is that right, Ryusei? Okay, so there is just sort of FOIL itself. I mean, there's the calculation itself, which is this is we get that this is equal to R times S plus B plus A times S plus B by the distributive law, because everything boils down to the distributive law. And then we apply the distributive law again. We get RS plus RB plus AS plus AB. Did I do it wrong? Maybe I did it wrong. Oh, I did it wrong. So the reason you're asking me like to explain this again is because I messed it up. Yes. So my bad. RB plus SA plus S plus AB. I was so excited about the reasoning that I didn't bother, that I messed up the actual calculation. So this is RB plus S plus SA. All right. Ryusei, did I fix it now? Yes, thank you, Ryusei. That's a very subtle way of saying, yo, Shu, you messed up high school algebra. My bad. Thank you very much. That's very mathematician of you. Thank you very much for that subtle reminder. All right, so everybody with me now? My bad. But oh, and then RB and SA, RB and SA and AB are all elements. Okay, so there. Let me go full screen so you can watch this again and see the correct version. And see, yes, I actually got it right this time. So that's what I meant anyway. So any questions before we do something calculational, which hopefully I will not mess up? Okay, so just quickly move on to that. Okay, so now let me move on to something which is both kind of concrete and calculational, but also doesn't sound particularly useful. I'm sure, unless you're familiar with this will not sound useful at first, but this is actually this particular topic of computation in f bracket x mod m of x. This is money, because what will happen. This is one of the most money-making things that we will discuss in this course, because this is what leads into how to compute in a finite field. And yeah, and it's one of the most useful things that you can know about as a sort of engineer having to do with communications, or things of that, of encryption, communication. Well, not encryption, but data compression, communications, anything having to do with transmitting signals. Knowing about finite fields is one of the most important things that one of the most important qualifications you can have as an engineer who knows sort of a mathematical engineer. So so even though it might not sound profitable at first, let's bear with me. So let f be a field, let m of x be a polynomial in f bracket x, and let r be the quotient f bracket x mod parens m of x. It's the ring of polynomials mod that initial polynomial m. So we have all these questions. How do we represent that come up? Suppose we want to compute inside R bar. Then we need some way of representing elements of R bar in a standard fashion. We need to be able to compute the ring operations of addition and multiplication in R bar, and also we need to be able to compute inverses in R bar. And in particular, we need to be able to compute. We need to be able to tell if a given coset. So remember the elements. So remember the element we just said. The elements. Now this is just recall. Nothing. Recall the elements of f bracket x mod parens m of x are the cosets of parens m of x. So how can we tell if this particular coset here, so remember, Ishan had that lovely description of cosets as being our original ideal shifted by something. So here our shift is actually a polynomial shift, shifted by a fixed polynomial f of x. So how can we tell if that element f of x plus parens m of x is a unit in R bar? And if it is, how do we compute its inverse? So yeah, we want to be able to write elements down, add and multiply them, and then take their inverses when possible. So let's remember how these problems are solved in Z mod M. So if M is a fixed integer and R bar is Z mod M, then the elements of R bar are represented. Yeah, I guess we'd have to sort of say that M is greater than 0. But elements of R bar are represented uniquely as integers A, such that A is between 0 and M minus 1. Oops, should say less than or equal to M minus 1. Abbreviating, so remember where A is an abbreviation for A plus parens M. Remember we had over here back in our, where M is 3, we abbreviated the cosets 0 plus I, 1 plus I, and 2 plus I as 0, 1, and 2. You represent elements as the point that these are the remainder, the possible remainder. You represent elements of R bar uniquely as the possible remainders mod M. To multiply two of those remainders mod M, you do addition and multiplication in the integers and divide by M and take the remainder. And so this follows from, actually because of our coset conditions theorem. And then you may also remember that A is a unit mod M exactly when the GCD of A and M is 1. And you, in that case, if you're lucky enough to have that case, you compute their inverses by Euclidean reduction. And the beauty of this abstract setup, so we went to all this trouble of doing this abstract setup, which is all very complicated and kind of deep, and it kind of hurts your head to think about it. But the beauty of that abstract setup is that if we think about this in the right abstract way, then computing inside the ring f bracket x mod m of x is exactly the same. I mean, there's a few new wrinkles to it, but in some essential abstract sense, it is exactly the same as computing in Z mod M. So again, computing in Z mod M is going to be the same as computing in this kind of complicated looking ring, f bracket x mod a polynomial is going to be exactly the same as computing in this other ring, Z mod M. Okay, so let's get down to some sort of details here. So let M of x be a fixed polynomial. So let f be a field, capital F be a field, let M of x be a fixed polynomial with coefficients in big F, and let capital I be the principal ideal generated by M of x. And and the theorem says that every coset f of x plus I has exactly one representative R of x, such that the degree of R of x is strictly less than the degree of M of x, and you compute that by finding the remainder R of x upon dividing f of x by M of x. So it's exactly the same way that the elements of Z mod M are represented by the possible remainders between 0 and M minus 1. The elements of f bracket x mod, so remember, this is really all about the ring f bracket x mod parens M of x. Each of those elements has a unique representative with degrees strictly less than M of x. Those are the possible remainders that you get when you divide f of x by M of x. So, oh, I see. I have a typo here. My bad. Given an element little f of x plus big F of x, we just define the reduced representative of the coset f plus I to be the unique representative of f plus I such that the degree of R the unique representative R of x of f of x plus I is such that the degree of R of x is strictly less than the degree of m of x. In particular, we abbreviate the coset x, just x plus I, where x is the variable here, as alpha in R bar, and f of x as f of alpha. So because, and we note that since m of x is an element of I, remember, this is the ideal generated by m of x, by the definition of quotient ring, m of alpha equals 0, because we're setting m of x equals 0, and so you sort of, as when you take that quotient, you replace the x with an alpha, and so yeah, since we're setting m of x equals 0, that means by definition m of alpha equals 0. We therefore sometimes describe alpha as a root of m of x. Oh my god, I get down to a concrete example. How far away are we from a concrete example? Okay. You know what? Let me actually sort of skip ahead. I will come back and sort of talk about the formalities of this. So let me actually just skip ahead and talk about, because I'm running a little late on time here. Yeah, about how you do this in practice. So, example. And this is actually sort of the only case that we'll actually be interested in. So let our ground field be f2, the integer is mod 2, and we're going to let little m of x be x to the fourth plus x plus 1. That's a polynomial with coefficients in f2, and I'm going to define f2 of alpha to be f2 bracket alpha to be f2 bracket x mod m of x. In other words, what this is going to boil down to is we're going to set a rule that alpha to the fourth plus alpha plus 1 equals 0. So what happens is that elements of f2 bracket alpha are polynomials in alpha, where we set the rule that alpha to the fourth plus alpha plus 1 equals 0. And so let me just do one sort of short example of how this works. So suppose beta is equal to alpha cubed plus alpha plus 1, and gamma is equal to alpha squared. So again, in practice, what happens in practice is that elements of this new quotient ring, f2 bracket alpha, are polynomials in alpha with the rule alpha to the fourth plus alpha plus 1 equals 0. And now, so let me point out here that as we'll see next time in more detail, I'll sort of justify this in more detail. But the idea is that when you see that alpha to the fourth plus alpha plus 1 equals 0, what you really want to think is that alpha to the fourth is equal to minus alpha minus 1, which, because everything is coefficients mod 2, is equal to alpha plus 1. And this is because all coefficients are still taken to be mod 2. And so if here's how you do this in practice. If we're multiplying beta times gamma, then we multiply this out as a polynomial. We get alpha to the fifth plus alpha cubed plus alpha squared. But what we want to do is we always want to sort of reduce polynomials of degree alpha to the fourth and higher by using the fact that alpha to the fourth is equal to alpha plus 1. Because once we see that alpha to the fourth is equal to alpha plus 1, we know that multiplying both sides by alpha, we see that alpha to the fifth is equal to alpha squared plus alpha. And so this we can replace this alpha to the fifth with alpha squared plus alpha cubed plus alpha squared. And then what we get is alpha cubed plus 2 alpha squared plus alpha. But again, I want to point out that the coefficients here are still taking mod 2. And so 2 is equal to 0. And so what we get as our final answer is going to be equal to alpha cubed plus alpha. All right, so let me write that out as an identity. The point is that alpha cubed plus alpha squared plus 1 times alpha squared is equal to alpha cubed plus alpha. Ah, all right. I did that like way too fast, and but I did want to I did want to, and I will actually. So trust me, I will go back to here where I sort of started skipping around a bit. But I started talking about adjoint alpha. So I will start there again on Wednesday. But this is just to finish up. I want to point out that this is where we're going to end up. So we're so what is it that I want you to eventually to get out of this? And we will start. We'll rewind to sort of the last 10 minutes and do that more slowly. But the thing I want you to get out of this is exactly this procedure. I want you to be able to take I want you to be able to represent two elements, sort of know what an element of F2 bracket alpha looks like. And I want you to be able to multiply two of those elements together and reduce them into their standard form. Okay, so I know that wasn't the most straightforward way of ending things, but we have negative 2 minutes left. So thank you for your patience. We'll start again. We'll start again on this part on Wednesday, and I will see you on Wednesday. So, bye everybody.